Go. Hi, I'm Mohammed bin Ashura.
I'm Siraj.
Hamza Al-Mawla.
And I'm Othman Amela, and today we'll be speaking about the Golden Gate Bridge, this suspension bridge in San Francisco.
Hello guys, today I'll be talking about the structural design of the Golden Gate Bridge. Okay, so I'll be talking specifically about the materials and the major structural components or elements that were used to build the Golden Gate Bridge. So first of all, the two main materials that were used to build the Golden Gate Bridge is the concrete and the steel. Okay, so these two tables that I got from the Golden Gate Bridge official website shows the amounts that were used, both for concrete and steel. Okay, these are the amounts that were used to build the Golden Gate Bridge at the beginning, which is between 1933 and 1937. But later on, they decreased the amount of concrete that was built by 25,000 cubic yards. So yeah guys, here are the major structural components or elements that were designed to build the Golden Gate Bridge. So I'll be trying to show you each and every part of them on the model, but I won't be able to do it for all the parts because some of them are not contained in the model because it's not a completed model. So the upper viaduct is so of course there are two upper viaducts from both ends of the bridge, and the piers I can't show you on the model, of course. The piers I can't show it to you on the models, even the steel arch. I can show you the pylons, which are these two. These are the pylons. The cables, of course, are these two, which are of course made of steel, and the trusses, which are supposed to be here, but I don't think it will be so clear as you can see here. These are the trusses. So yeah.
Now I'll be speaking about the structural behaviour of the Golden Gate Bridge. We've got I'll be speaking about the main external forces on the bridge. We've got three types of loads. We've got the dead load, and the live load, and the dynamic load. So basically the dead load, as we can see here on the bridge, this is the bridge without anything on it. So basically just the basic elements of the bridge and the self-weight of the bridge. Second of all, we've got the live loads, which are due to the live traffic moving on the bridge, also due to the environmental factors such as the weather conditions. So for example, here we've got a sunny day and the material inside the bridge expands. Also here I've calculated the total live capacity of the bridge. So we've got the total live capacity is 1.6 times 10 to the power of 8 newtons. Also, the third thing is the dynamic load, and this is like the extreme environmental factors on the bridge. So here we've got like an earthquake, and the bridge is like moving about, and yep, that's about it.
Cool.
Now I'll be speaking about the support reactions and deflections on the bridge. Basically, there's two types of deflections. There's a maximum upward deflection and a maximum downward deflection. Maximum upward deflection occurs in the midspan of the bridge, and this equates to 3.3 meters. And the maximum downward deflection is due to the maximum live load at the center of the bridge, of the bridge span, and takes into account the maximum temperature that extends.
Whenever you're talking about a bridge, you can't ignore wind and temperature. When you're talking about the wind, let's come before building the bridge. All experts said that it's impossible, it's really hard to build a suspension bridge at this length in this location, because it was the first at that time at that location. Another problem was that the bridge catches too much wind due to the thick depth of the deck, which is 7.6 meters. Engineers actually used wind tunnels to improve the bridge due to the winds and stuff, and they successfully did it. The bridge was closed about 5 times due to bad weather. On December 1951, the bridge was closed due to 112 km/h wind gusts. which made the bridge sway 4.3 meters in both directions. That's about the wind. When you're talking about temperature, the temperatures there ranges between 4 Celsius in winter to 24 Celsius in summer. The overall temperature change does affect the bridge, and also the difference in temperature between the top of the deck and the bottom of the deck.
Okay, so far my colleagues have talked about the external forces on the Golden Gate Bridge. Now in this slide, I'm going to talk about the internal forces of the Golden Gate Bridge. So the first image on the top left, as you can see, is a cross-section of the bridge, which shows the maximum stress on the bridge along with a few more figures. Now I'll explain if you come towards here on my diagram. Imagine if you take a cross-section through the bridge. A cut through the bridge, this will reveal the cross-section, where B is along the bottom and D is along the side of the column, if you imagine, of the cross-section. And that is how we calculate I, which is BD cubed over 12. We need I to calculate the maximum bending moment, which is the maximum stress, 275,000 kilonewtons per meter squared, multiplied by I divided by Y. And the answer is, as you can see, 71 meganewtons per meter. So that is the bending moment on the bridge we calculated. Now, onto our second image, which shows the tension and compression forces on the bridge. I'll just show you on my model first. The tension forces move away from each other in the direction of the cables away from each other, and the compressive forces move towards each other in the columns, and this is again displayed in the image again. For the blue arrows, the tension forces are moving away, and the compressive forces, the red arrows, are moving towards each other. They represent the compressive forces. Okay, so that is really the sum of the internal forces of the Golden Gate Bridge. Now, these are some references for our sources from which we generated this presentation. And that was our presentation on the Golden Gate Bridge. Thank you very much.